What is this, week 7? I think that's right. It's the 7th meeting. Week 7, all right. Great. So here we are on the untitled lecture. Click to add title. But this is so last week, we discussed a few different tests, but mostly we were talking about, I think we only discussed 2 different ones. We got the one sample difference in means test and the one sample difference in proportions test. We kind of talked about how there might be non-parametric tests later, but those are the 2 that we discussed. And we also finished up some of the previous ones. So we discussed some concepts about hypothesis testing in general, talking about tails and different types of error. But in terms of the tests, can anybody think of a scenario where we would use a one sample difference of means test, whether it's a Z or a T test? When would we apply that? Or when would that work? One sample difference of mean test. What's that for? If an example helps you in your answer, then that's okay. When would we use a one sample difference of means test?
When you're comparing 2 means? Are you comparing a sample mean and population mean?
Yeah, and that's exactly right. A sample mean to a population mean. Now, we may not actually know what the population means. It may be a theoretical population. But we have one sample mean, and we've heard that the population mean is this, from whatever. Whatever it might be, that source might be. But we're comparing that sample mean, which is a bunch of real numbers that we actually got, and the population mean. And oftentimes we don't actually know the real population mean, but we're seeing if our value could reasonably be taken from a population mean that had this theoretical value. So we know that the sample is going to have a different mean than the population. Okay? But if we have a population and we theorize that the average height of these small people that live in a certain part of South America or something is, 5 feet. That's the average height for a male in that population. Then we could use the one sample difference of means test to see if this sample that we took, if they could possibly be from that theoretical sample. That's theoretical population.
So you're mainly using it just to kind of see if you're heading in the right direction before you move on to something more? Or would you ever just do that and stop with that?
Yeah, you might do that and stop with that. It's although I would say that the we're going to talk about today is a little bit more common. But if you're dealing with either a true population, let's say you do have a true population value, you do know the population mean, or maybe that population mean is historical. Like you have a population mean from 10 years ago, and you have a sample that you just took today, and you're wondering if this sample is from the same population. In other words, maybe your theory is that the things have changed over time. And so you're saying, does this current sample that should be from that same population that was 10 years ago, is it still statistically different, or is it statistically different, or is it the same population that existed 10 years ago? So like if you had a theory that the people are getting taller over those 10-year periods, you could take another sample of a population, or, you know, the second one, the one on difference of proportion, you could see if somebody's opinions on something. So if 10 years ago, you know, 38% of the people believed that climate change was real and it was affecting our planet. And then today you took a sample and you found out that 42% of people believed that climate was changing, but you had a population from the first time, not a sample. Population from 10 years ago and a sample from today, then you might wonder, could this sample that I took, is it just chance that I got a little bit higher this time? Or could it really be that the opinions haven't changed? Then I could use the one sample difference in proportion test. Now my population would probably have to be fairly finite to have had a population statistic 10 years ago. Like maybe I was just concerned with all of the faculty at USM. Okay? And so I had everybody 10 years ago. I got all the faculty from USM. Whereas this time I only took a sample of 20 or 30 of the USM faculty and posed the question, asked that question to them. So in that case, I'm comparing a sample to a population. Now it is a subtle difference, but what we're going to talk about today is essentially very similar, except for both times it was a sample. 10 years ago I took a sample of 30 USM faculty, asked them the question. Today I'm going to take a sample of 30 and ask them the same question and compare those two results. So the only difference between some of the tests, we actually are going to talk about a few other tests, some non-parametric tests. The only difference is that one of the two things being tested was a population last week, whereas today they're both samples. But there are actually three different, and we'll talk about these. There are actually three different scenarios. What if you can assume that both samples had the same variance? Then you use a slightly different formula. What if you can't assume that both samples had the same variance? Then you use a different formula. Then the third scenario is, what if in both samples they were the exact same observations? That might be hard to do in our two sample example of 10 years ago. 10 years ago, the people on the faculty might be different, right? Than they are 10 years in the future. But let's say for our scenario they aren't. If we found the same 30 people 10 years and asked the same 30 people 10 years later, that's a matched pair. So those are the three scenarios. So two samples, there's kind of like two scenarios with a subsample on one side. So we've got, sorry, I meant to turn it down. We've got two samples where we just took two different samples, and they may be even two different groups of people, so they couldn't be matched pairs. So, one of the examples we're going to work through today is we might select a number of countries and then select another number of countries and compare their results. Okay. That would be looking at non-matched pairs. But if we had a bunch of fish that we harvested, we called that a sample, and we measured them, and then we fed them a certain diet over a 10-week period, and then we measured them again, that'd be a matched pairs test. the difference there is whether or not they're matched or not. And then if they're not matched, can we assume that the variances are equal or not? So those are really the three types of tests that we'll go over. They're all under these 2 sample difference tests. What happens if we take 10 samples or 4 samples, whatnot? Well, there are tests for those, and that's where we're going. But today, we just got the 2 sample difference tests. I'll talk about that when we get to it. Not next week, but after spring break. All right. So the key here is that we are looking at differences that exist between 2 random and independent samples. They can't be dependent on each other. So, the inference here is that samples drawn from 2 truly different populations will have a different mean, and the way that we can test that is to compare their means and their variances. So here's the example from the book. Amazonian farm income between two municipalities, forest clearing rates between 2 types of land partitioning systems, and assaults between 2 neighborhoods adjacent to campus. So these would all be examples of something that would work well in a 2-sample test. We're not comparing the population to a sample, we're comparing 2 samples to each other to see if they could be the same population, if they're significantly different populations. So in this last one, is the crime south of campus any different than the crime north of campus? We could take a sample, and of course they're going to be different, but how different are they statistically? All right. Now there are both parametric tests for normally distributed data and data with a lot of samples. It's called a Z or a T test. The only difference here is that the T test means that we didn't have more than 30 samples. Once you have more than 30 samples, you can use the Z test. There are non-parametric tests. The non-parametric tests will only work on ordinal scale data. So in our example, let's say that trying to think of how we could change the so let's say we could subdivide the areas south of campus and the areas north of campus, and we had like 5 areas north of campus and 5 areas south of campus, and we took their overall ranks and said this area had the highest crime rate, this area had the second highest crime rate, the third highest crime rate, and so on, all the way to number 10, because we had 5 in the south and 5 into the north. Okay, that's ordinal scale data. So we have to be able to transform our data to ordinal scale data to use a non-parametric test, and then we just compare ranks. We have another slide on this, but it's reasonable to assume that if the areas in terms of most crime, 1, 2, 3, and 4, were all north of campus, and so was like 7, 1, 2, 3, 4, and 7. And then south of campus, you had 5, 6, 8, and 9. There would be less crime south of campus. Okay? But what if it was a little less ambiguous? You had 1 and 2, and then 3, 4. So when we compare the ranks, there's a statistical test for that, and that does not require that the data is normally distributed. Okay? And it doesn't even require us to know a lot about the population parameters. So that test is called the Wilcox Rank Sum W test, sometimes referred to as the Mann-Whitney U test. All right, so that is the test for if we know our data is not normally distributed, we can convert it to ranks on ordinal scale, and use this test, and we'll talk about it in a little while. Okay. All right. So in all of our tests, we're going to calculate this z test statistic or the t test statistic. And in this case, the numerator is very similar to what we talked about last week, except for we're not comparing population mean to sample mean, we're comparing two sample means. So this is looking at the difference in the two sample means. It's just subtraction. So as the numerator increases, you'll get a bigger, as the difference between the two sample sizes increase, you'll get a wider difference in the numerator, a bigger difference, a bigger number in the numerator. The denominator is still, the standard error, but the standard error is calculated in a little bit different way. Here's the theoretical standard error. In other words, if we know the population statistics for both of these samples, which we're kind of progressing into a point where that would be very, very rare. I don't understand how you'd have the population standard deviations. If you did, then you would know the population means, and then you would have used them and just compared them straight up. We don't have those, so we're going to estimate this value here. But this is the formula. The formula is just the variances, which is the standard deviation squared, divided by the number, added up together, and then you take the square root of the whole thing. Okay. So similar to what we've done in the past for calculating standard error. Now we're just combining two, almost as if we're taking the average of the two. Because the standard error before was just the standard deviation squared divided by n with the square root. Right? But now we're adding them together and taking the square root. And the t-distribution is not much different, other than we're going to look at the t-tables rather than the z-tables. And basically we use the t-distribution when we have a small n value. Something that's not covered here, at least not in my notes, is that when we go look up the t value, how do we find the right t value? Because the t value requires us to calculate the degrees of freedom. Okay? I think it's covered in your book. But I'm pretty sure that it is just the two n's, n1 and n2, added together minus 2 instead of minus 1. So you're just taking both n values, adding them together, and subtracting 2. But the book should have that number, right? I mean, you'd think it would be included there. I don't see it, but we'll come back to that. Kind of like the denominator of 10.4, but that's just the pooled variance estimate, which we'll talk about in a second here. All right.
So that gives us a degrees of freedom.
Right. When you're looking it up in the table. Okay. So this is what I talked about before. If we can assume that the two variances are equal from the two populations, in other words, they're two different samples and they come from two different theoretical populations. If we can assume that they're equal, then we use this pooled variance estimate. And basically, this is to calculate the standard error because we don't have the population standard error. So we're calculating this denominator here. So we can assume that they are the same. Then we can use this formula to come up with a pooled variance estimate. basically all we're doing here is taking the two standard deviations and kind of averaging them by combining them arithmetically. So we're taking the two standard deviations squared, and then we're taking the total number of observations, because we're saying, hey, you're all the same. You're all part of the same group. We're going to average you together and take the square root to return it back to being in the same units. So standard deviation is in the same units as whatever you're measuring. Variance is in those units squared. And so when we square them, add them up, divide by the total, and then take the square root, we're returning it back to those units. So that becomes our estimate of the pooled variance. But we're not quite to standard error yet. Okay, we need to take the pooled variance estimate and multiply it by the square root of 1 over the sample size. So when we call it pooled variance, we're basically taking the variance from one sample, the variance from the other sample, and putting them together, averaging them together. And it's not an arithmetic average, it's squaring them, dividing by the total, and then taking the square root. But it's similar to taking the average, and we come up with a value. So if we do this, we're basically saying that we're more sure about the variance. So we're going to always get, we're always going to be able to accept the null hypothesis with a little bit less, well, actually, it's going to be a little more often, with a little more confidence. We'll be selecting or accepting the hypothesis more often, because we're tightening up the variance. And maybe I should have had a diagram here, but you know what we're doing. I'm going to draw another bad drawing. Okay. Let's say these represent the two samples that we took, and this is the overlapping area. So what we're trying to do is come up. These represent the probability that the mean is a certain value. The highest probability is right here. Okay. So these are the two samples. But the mean could be anywhere along here, anywhere along the z distribution. And the z distribution tells us that the probability of the mean being like right here is, this value, this area right here. And then same with this one, probability of the mean being right here is this value. All right, so if we were to tighten these up, which is the pool variance estimate would tighten it up, we'd have less overlapping area, maybe no overlapping area. But since they kind of go out forever, there are values out there. Okay, but that's what we're doing. We're tightening up the variance, but we're assuming that they're equal. If we assume that they're not equal, they get bigger. So the basis of those get bigger, and so there's more overlap. So there's less certainty that they're from different populations. All right, so this is the single variance estimate. The estimate of single variance there is just calculating the separate variance estimate. The separate variance estimate is simpler to calculate, but it results in a larger value for the variance. All right, we can. This is just the figure from your book, but it's important to point out here that this is used to compare two independent random samples. Okay, you can hypothesize that they are equal. Okay, that's always going to be your null hypothesis. Is the crime So the null hypothesis for our scenario is that the crime south of campus is equal to the crime north of campus. Or in our scenario with the height of the people now is the same as it was 10 years ago. Okay, and we have two samples. Or later when we get to, there's a proportions test for this. The proportion of professors that believe global warming is impacting the planet has changed. It has not changed over the last 10 years. That would be the null hypothesis. And then you can have a two-tailed scenario where you say so each of these is a null hypothesis. So one null hypothesis is that the proportion of people believing in the impacts of global warming has increased, or it's decreased, or it's just different. Those are three different things. And basically, if it's a two-tailed versus a one-tailed, you'll have less. You'll have a different cutoff for your p-value. What's that? Sorry.
Did you say the HA one? The null?
That's the alternative hypothesis.
Which one's the null?
The null hypothesis is this one. You only always have one version of your null hypothesis that they're equal in this test. And then the alternative hypothesis is either that they're just not equal or that they're higher or lower over the two different samples. Okay, and we'll work through an example of that in a second, but here is the Mann-Whitney, or the Wilcox rank sum test. In this scenario, the data is available in ranked or ordinal form. That's a requirement. What that's saying is that's a requirement. If your data is not in ranked or ordinal form and you want to use the Wilcox rank sum test, you have to convert it to that format. Okay, so we're not concerned about sample means or sample variances. So this is good for non-normally distributed data. If it's not normally distributed, you can downgrade it to ordinal data. Almost all data can be converted. I mean, it's hard for me to think of a scenario where you can't convert data from raw numbers down to ordinal numbers. All right. So the distribution of your two samples is still assumed to be the same shape. That is one of the assumptions. One of the things that, what if you have a very small set of samples? In the scenario I gave, where we only had 5 samples north and south of the university, that's an example. We could put that into a difference in means test, but since there are only 5 samples on each side, our degrees of freedom are going to be really small. Even in the pooled variance scenario, we had 5 and 5. We get 10, subtract 2, it's going to be 8. So there's a lot of uncertainty. And so for small sample sizes, or for non-normally distributed, it's a good one to use. So if we look at this, and I already kind of described this, it looks at the mean ranks. So it takes the sum of all the ranks. So in our case, if we just had 10 areas, the sum of all the ranks is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, right? I don't even know what that is off the top of my head, but somebody probably has a formula for doing that. And then you basically, once you figure that out, that's this WI term, you compare it to the W bar I term, which are the mean ranks of one of the two sets of values. So you just take the mean the rank, and then you multiply it by this term, which just gives you the value, and then you calculate the standard deviation as this formula. Or through an example. In fact, we could work through that example that I just talked about really quick. File, new. So this is just we don't know for sure. We'll just call this north and south. Okay. And then we'll have each neighborhood ranked in terms of their crime. So if we had 1, 2, 3, let's make it not quite as easy, 7, 1, 2, 3, and 8. So that would leave 4, 5, 6, 9, and 10. So those are ranks. So we would have to know the actual crime rates for those areas. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they're all. You can like if you have two that have the exact same value, the math will still work out to like average those two. So you can have like a 1, 2, 3. Let's say there were two that were tied for third. You could have a 3.5 and another 3.5, and then move on to 5 at that point. So you can average the 3 and the 4 ranks, and the math will still work out for doing that. Okay. All right. So in this scenario, we would first calculate the sum of all the ranks for sample I. Actually, I'm going to make this a little bit different, because this is the way the data would probably look. It would probably look like this. And they actually don't have to have an equal number of samples from each either. I'm just doing that for fun, but like let's say you had 7 in the south and 10 in the north or something. So the sum of all these values is W. So that's the sum. I'm going to call that W right there. Okay. That's W. And then WI, okay, is that mean of rank WI is equal to NI. See if we get an example. Yeah, so there's an example, but with different data. The data from chapter 10. There's an example on page 162. So it shows you how it's just the number of samples. You're just messing around with the number of samples. So Ni, in our case, is 5. I think one of the things that we should do to make this a little bit easier to understand later is to actually add another value in here. Sorry. 11. Okay. So I added another value in because now N, 1, 2, 3, 4, 5, 6 values, and S has 1, 2, 3, 4, 5 values. So because that way we'll be able to see that we'll be able to see how it goes into the formula. So the formula is WI is NI, and NI just means the one that you're saying is different. So you could just pick one. It doesn't it doesn't have to, you'll get, the math will work out either way. But you need to pick whether or not you're testing, is this one different than everything, or is this one different than everything? So we'll start with N, the north areas. So we take the total number in the north, which is 6. So this is, we're going to call this W little I. So we're going to say that is equal to 6 times the sum of 1 plus N plus 2, which is 6 plus 5, because there's 5 of these samples, plus 1. So 6 of these samples, 5 of these samples, and then you just add 1, and then you divide by 2. Make sure I'm getting my parentheses right. Probably don't need these parentheses, but I'm always a little paranoid that it make sure it does that first. And then, oh yeah, Excel will get mad if I don't actually put a multiplication sign there. All right. So I get 36. All right. So that's that value. 36. And then finally, I need to calculate the standard deviation. Now, the standard deviation value, notice that it doesn't have a WI or an NI in there. It just has just has the two terms. So I got S, W, and it is equal to, this one's a little bit harder, square root SQRT of 6 times 5, which are the two sample sizes. So 6 of these, 5 of these. And then we multiply that by N plus 5 plus 6 plus 1 divided by 12. And again, I'm going to put my little parentheses here and here. And I think that should work. 6 times 5 divided by 12. There's got to be a multiplication sign right there, or Excel will get mad. Okay. So that's the formula right there. It's the same formula that's on page 10.9, the standard deviation of W, standard deviation of W there. That's the formula in 10.9. All right. All right. So now we just calculate the Z statistic, which is equals, oops, sorry. I think I messed up. There we go, yep, I just messed that up. So the actual Z statistic is WI, which is the sum of the ranks, equals this minus this. Oh wait, sorry, I did mess up a little bit, but we're going to fix it. Okay, and then divided by the standard deviation, this one. Okay, the place I messed up is that this number. So yeah. This still needs to be the sample of these, just the north ranks. Because you're comparing just the north rank to what they should be. So this value isn't the sum of all the values. It's the sum of just these values. And those values are right. Okay. All right, so that makes a lot more sense. So this value here is telling us what the actual sum of the ranks are. This is telling us what the sum of those ranks is expected to be if these ranks are truly random. And so then this is the standard deviation of the ranks, and this is the z-test statistic. We probably don't even need to test that. Okay, if this is a z-value, how many standard deviations away from the mean is that? Yeah, it's really, really small. It's up in there. So we probably can't reject our null hypothesis with it, accept our null hypothesis. But if we did want to pull the value off of there, we could go back to the z-table, and we got that z-value. So we got a point. What is that? 0.7. What is it? I can't. Oh, it's right here. 73. 0.73. We don't have anything better. So we got 0.2673 from one side of the curve. 0.2673. I'll write that down. 0.2673 from one side of the curve, and then we double that. Oops. Times 2. So that's the area under all of the curve. We subtract that from 1 minus this is 0.46544. So we're saying that, and if we had a p-value of 0.5, we could compare that value and 0.05. It's way out, it's way over there. We have to accept the null hypothesis. Or not reject. What's that? That's 1 minus this. This is this doubled. Yeah. Now we could also remember from before. Yeah, it returns the one-tailed p-value of a z-test. Oh, that's. Now what's the name of that function? The z lookup function. What did I forget it? We talked about it earlier. Normal, right? Normal distribution, returns the normal distribution for the specified mean and standard, normal inverse. Here's the, we don't have, we don't have the same values. It's a little different. Yeah, because we don't have the same. This test isn't the same as the one we did earlier. If this was actual means, it'd be different. Yeah, we got that value. We compare that value to like 0.05 or 0.02, whatever we want. If we want to, we have to choose whether we're going to reject it at 0.05 or 0.10 or 0.20, but that's way bigger than all of them.
A 1-tailed or a 2-tailed?
Well, you can make it either one, but I kind of framed it as a different.
Oh, just they're not equal.
Yeah.
So the alternate hypothesis is just they're not equal.
Right.
And that's what makes it 2-tailed.
That's what makes it 2-tailed. No, we doubled the value because the z-table in the back of this book on page 303, the z-table actually gives us the area under half the curve.
Okay.
there's different ways of actually getting what you want to get, but what we want to get is the area from Z over. That's what we want to get.
From Z
To infinity.
to, okay.
And so, I guess another way to do this would be to take this number right here and subtract it from 0.5, and then double that. See this number right here? So this number, or sorry, 0.5 minus this number is 0.23 equals this times 2. So yeah, I guess you're right. We do need to double it. So I was looking at it a little bit differently, but since it's two-tailed, it does need to be doubled because it's two-tailed.
Okay, yeah.
You're right. So this number would be our cutoff, not our cutoff. This number is our critical value. But either way, it's bigger than 0.1 or 0. Whatever our p-value is that we're comparing it to. In both cases, it's bigger. But if it was one-tailed, this would be our value. And we compare that to, and you know, you should come up with the value you're going to compare it to beforehand. What p-value you want to compare it to. You don't look at it and go, anyway. But that's the one-tailed, that's the two-tailed value, the area under the curve. You can compare it to your, to whatever value you decided you were comfortable with. It's the probability of getting a type 1 error is another way to say that. And that's why we covered those errors in the book. This one from the Z table for 0.73. So on the Z table, 0.73 was 2673. That's on page 303 in the book.
So for a two-tailed test, you get the area from the Z table for whatever your test statistic was. Subtract that from 5 and double it. Or subtract it
From the Z table that's in our book. Yeah. You subtract it from 0.5 and double what you do for a two-tailed test. You don't double it if it's a one-tailed test. All right, let's change the numbers up slightly and recalculate it. So I'm going to basically take this whole thing, copy it into a whole another sheet, and this time we're going to make the north value steal 6, and we'll change that with 11. So now the north has 1, 2, 3, 7, 8, and 6. The south value has 4, 5, 11, 9, and 10. Okay? Now, all these numbers automatically recalculated for us, and we get a value of 1.64. So somebody look up 1.64 on the Z table and tell us what we get for that value, the new p-value. It's not going to be 0.2673. That's the value from the Z table. 0.4495. Okay, and so now this value will update. So this is basically 0.5 minus this value is 0.0505. So if we're getting really close to rejecting the null hypothesis there. If it was 0.1, okay. If we're interested in making the right decision 90% of the time, we could definitely reject the null hypothesis. If we're interested in making the right decision 95% of the time, we're right on the border, okay, in a one-tailed test. In other words, To answer the question, is the crime south of campus less than the crime north of campus? If we're interested in being right 95% of the time that we did a sample like this, we were right on the cusp. Okay? We probably want to report it. I mean, it's almost significant, basically. We're still not significant on two-tailed. Is it different? To answer that question. All right. So that looks like, I mean, just looking at it, it does look like there's some pretty big differences. But we're only on the cusp of it being significant. Interesting. Probably one thing is that we don't have a whole lot of samples, but let's try to change just one more that might be. Let's change this 4 with the 3. Just swap the 4 and 3. So this one's going to be 4. This one's going to be 3. No, wait, let's go in the other direction. Let's swap the 4 and the 5 and the 6. So this will be 5. This will be 6. Okay, now we're at negative 0.8257. 882 would be 4656. Right? Am I getting the right number? I'm going to go 825, so I'm going to go 0.4664. It's a little bit more because it's rounding up. What did I say? 4664. So now, yeah. So now, on the one-tailed scenario, we're well into 95% confidence. I mean, 95% of it. We're well into accepting rejecting the null hypothesis. If we're interested in being right 95% of the time that we take a test like this, then we're at 0.3. We're getting close in the two-tailed scenario. I would think in this scenario, the one-tailed makes a little more sense. Because we're looking at an obvious change, which we think there is a difference. We could say, yeah, crime down here definitely looks higher than crime up here. There's less differences in the max. You can see how different the expected value is. This is the expected value of the ranks, and this is the actual value of the ranks. In other words, if they were more normally distributed, not normally distributed, more evenly distributed. I'm going to do this just to show, make it look like. I'm going to show you how if we did do 1, 3, 5, 7, 9, 11, and 2, 4, 6, 8, 10. See how those become they can become exactly the same in this scenario. The reason why they become almost exactly the same is because the value of the north ones, the average rank is the same as the expected rank if the values were just totally random. The expected value would be that you'd have an equal ranks. Now, if we did have exactly the same amount of samples in each group, we wouldn't have to do all this math. The math is about saying, well, these ranks are higher than these ranks added up, but it's because there's more values over here, and that's why we needed to do all that math, because we need to figure out what the average value is. So see, it's 6, the number of samples, times what the average value should be. So it's like a weighted average. That's what that number is. So that's kind of a cool. statistic or interesting statistic. Okay, so that's an example of the Whitney, and that was totally made up data, by the way. So I don't know what the crime statistics are. North and south of campus. Just so you know. What's that? Yeah. So nobody watched the video and say, well, the crime. Of course, I have 3 different versions of it. Okay, so this is an example from the book. We're going to work through here. So here they're looking at the evaluation of female participation in the labor force. What do you think are some of the factors that influence whether or not females participate in labor? I think they're economic drivers or cultural drivers or so education. So in a more educated area, there may be more women participating in the labor force. Is that what you're saying? Okay. Culturally, do you think there's any drivers that impact that? In some areas, and maybe there's interaction. Like in some areas, women don't get educated because of cultural reasons, and therefore they don't participate in the labor force. Okay. In some areas, they don't get educated, but there's still like a lot of people in the labor force, right? Because there's lots of, like, maybe in tourism in areas, there's lots of maids and people working in restaurants. There's lots of unskilled but still, lower middle class incomes to be had. And so there's lots of women participating in the labor force, but not necessarily, making a whole bunch of money. And so anyway, I guess what I'm trying to say is that there is good reason to think that in more developed countries versus less developed countries, it may not necessarily have much to do with telling us about the labor, or vice versa. We might not expect there to be more participation in more developed countries than there is in less developed countries, but we might. Okay, I don't know what you all think, but that's what this scenario is looking at. Is the participation in females. So look at this map. It kind of shows. So look at Canada. It's very high, right? Is Canada a more developed country or a less developed country? More, right? Okay. But we've got a number of countries down here in sub-Saharan Africa, Botswana, Mali's over there. We've got Tasmania. I mean, not Tasmania. Kenya, and I think that's anyway. That's Kenya, right? That's Kenya. I mean, anyway. Yeah. Okay. So we got all these countries over here, Madagascar, and they actually have pretty high labor force. So does Brazil, female participation. And then you've got some countries in between, because most of these countries we consider definitely less developed. Got some countries that are probably considered less developed, but a little bit more higher on that scale. We've got more developed countries. So it doesn't seem to be a big correlation, right? You can even look at the data here. I'm going to skip to this slide. So this is more developed countries and less developed countries, and then they're where they fit on this scale of female labor force participation. So you actually have a tighter group here, but the mean is almost identical between these two groups. So we might want to test, are they different? Okay. So using the data that they provided, this is the work table that they work through. They get a t-statistic, and the t-statistic comes out with a p-value in each case, 0.462, 0.528, 0.657. This is 89, 90, 2009. In each case, those values are large enough to what? Do we accept the null hypothesis that they're equal, or do we reject the null hypothesis with those p-values? Even if our alpha value was 0.1, we still would what? Reject the null that they're equal? These are the values they looked up, and they calculated the area under the curve going out. These are all two-tailed values, by the way. So the one-tailed values would be half of those. But still, even this one would be 0.2 something. Right? So compare those to what we just talked about in the Mann-Whitney test. Okay? Did we reject or accept it here? That they're equal. Do you remember?
Accepted.
In this case, I think when we first did it on the very first one, that one, we did what? That's one where we accepted it, and we said that they were equal. But then I kind of played with the numbers a little bit. Well, that's one. Okay, this one's all messed up. This slide right here. I should go in and fix the p-value there, but see, that's 0. So this is actually 1 or 0.5. Or sorry, no, this would be 0. Yeah, that's right. That's what that would be. So anyway. Okay, so here, this value is 0. Maybe we're not making the connection to the last part very well. Okay, so let's look at the two-tailed here. 0.06. That's a number that's actually really close to 0.05, which might be the cutoff. So that's one of the reasons where we might have a question mark. Okay, if our number is bigger than the alpha value that we choose, then we are accepting, not rejecting, the null hypothesis. So we're saying that they are equal. Okay? Or, yeah, we're saying that they are equal. So if our number is bigger. So in this case, in this case here, these numbers are definitely bigger, whether or not we choose 0.1, 0.05, or 0.001, or 0.01. Those numbers are all bigger than those. And that should make sense, because if you look at this doesn't look like there should be a difference, right? I mean, the means are almost identical. Yeah, the standard deviations are different, but it's really hard to say that they're different than each other. They're from different populations. It's just that we selected out some that happen to be tighter than the other. It's really about comparing the means, and then the variances, kind of seeing if they're different. So over time, it seems like the two-tailed p-value is actually increasing, which means we're moving further away from them being significantly different from each other. In any case, you usually just say you reject or accept. But in all three of these cases, we accept our null hypothesis that they're equal. Maybe we should have actually stated a null hypothesis. Does that make sense? Or?
That makes more sense.
Okay. All right. Each of the 3 years, the average, So even for each of this was the null hypothesis. Each of the 3 years, the average female labor force participation rate of more developed countries is not different than the average female labor force participation of the least developed countries. And we accept that because these values are so large compared to the probability of making a time. We just choose the probability of making an error. That's what we choose. And no matter what we choose, unless we decided that we only want to be right, let's say 60% of the time, then we could actually reject null hypothesis, at least in 1989. But only in 1989. And nobody uses 60% as their cutoff, right? But if we were interested in only, so what we'd be doing if we did reject this year, then we would be saying that we could be wrong. 45 was 55. 55 for there's a 55. There's a 0.55 probability that we were wrong in rejecting that. Or no, sorry, 0.45. 45 plus 55 is 100. Okay. Now, since there aren't that many samples, particularly in the more developed countries, it might be better to do a Mann-Whitney test. And the book author gives you the data. The problem is that in the data, he doesn't say which ones are more developed or which ones are less developed in the data that he gives you. So it'd be nice to actually be able to work through this. And we'll work through a similar problem, but I don't know which 15 countries they chose for the more developed countries. So I can't replicate this exact test, but we'll do a similar one. But we can look at the thing that he worked through. So he's got 15 and 45 as the two ends, and he's got the sum of the ranks. This is the part where we couldn't do this ourselves unless we know which 15 are the ones that he chose. We could kind of guess, like we know Canada and the USA are 15. Probably most of Western Europe is in there. But what about China, for example? Probably less developed, but who knows where he put it. So that's why we can't reproduce this from the data. And we'll look at the data in a second. I'll show you what I mean. So here's the sum of the ranks. There's the average rank. So there's the average rank for N, and for more developed, the average rank for the less developed. Now, those ranks are really, really similar. Okay, but if we want to do the Mann-Whitney test, we could take we have to choose which one we're going to test. Either one is fine. You're going to come out with the same p-value at the end, but you have to choose one because your math will work through to choosing one. So if we choose the more developed countries, we get 473. Then we have to calculate our expected value, and that is this one. So the expected value is 457.5. That's the expected value. And they're close, but they're actually not like identical. Calculate the standard deviation, and then plug these values into the formula, and we get 0.273 as our t-value. And again, we take that t-value, we go look it up in the table, and we come up with a 79.12 two-tailed p-value for. This is not the value directly drawn from the table. Okay? This is the value you take from the table, you check. So we're finding out the area under the curve on both sides. So 1/10 would be half of that. But think about how much area is under the curve. 1. So how much is outside of those areas now? In the middle, it's hardly anything, right? What's 0.79? Like let's just say it's 0.8. So there's only 20%. So we're talking about here is a value that looks like, that's really bad. But anyway, it's the mean. So 20% might be just this area right here. And so all of this area is the area under the curve, the area that we found. That's 0.79. And so if our alpha value, our probability that we want is maybe 0.05, All right? We're so far away from that that our p-value is so much higher than that there's no way we can reject the null hypothesis. So it's even using the Wilcox rank sum test, the conclusion is that that we should accept that there's no significant, that's the way he states it. The very last sentence, thus we must conclude there's no significant difference between more developed countries and less developed countries' female labor force participation rates. So that's the conclusion that you get from that. Okay, we still got plenty of time here. So what I did want to do is just work through an example, because if we go back to this slide, where I think there might be a change. Okay, let's look, for example, at Europe and Africa. Okay, or let's just do Europe and Africa. Does it look like there's a difference in female labor force participation that might be between these two? I mean, there might not be, because look at all these values. But there's none of the low values that there is in Northern Africa. It would be nice if there was an identifier for the Middle East, if there is, because that would definitely produce a result. Oh, we can make up our own identifier. Okay, so let's do that. So this is going to take a little bit of GIS and a little bit of calculations. Okay. So I'm going to add the data that I forgot where I put it. I think I put it in C temp QM. So you can download this data from the course website. It's called Book Data. All right, so I don't know why this is called lifegood.shape. Seems like a weird name. Life is good. But we have it's basically got the female participation rate mapped here. In the data. This is the female participation rate. So if you read this as in this country, whatever it is, 73% of women participate in the labor force. And you might be asking, what does that mean? Does that mean they work full-time, part-time? I don't know exactly. I'm sure that metadata is written down somewhere. But we can map this by just going to symbology, and let's pick the most current year, 2009, and map it. I'm going to map it on a. Actually, that's not bad. All right, so those values look different than 2009 than what they've got, right? I wonder if those values are because Tanzania. I kept saying Tasmania. I know it started with T. 56. Let me see if these values are the same as, or if they just totally have different values. MNOP. There it is. That's the same number. Well, Okay, Yemen on here has a value of like 20 something. Let's see if that's the case. Which one's Yemen? Oman, there it is. And we have a value in 2009 of 64. So these values must not be the same as the book data, or at least they seem a lot different to me. Which is too bad, because which country is that? San Marino, 82. What's the lowest? Lesotho. Well, it doesn't really matter that the book data. I don't understand where they're getting that data. I'm not sure what this data represents. Selection, clear selection. So I don't think it's the same as the female labor force data. And it's got Europe and North America have similar colors, or whatever it is. Maybe it's the high and the low developed cutoff or something.
It looks like maybe for the
Well, I think it's more than that, because the numbers don't even match up, and I do not see another value that could represent this looks more like it's a map of the development of the countries to me. And even this value says that it's in the folder called female labor force, but it does not look like it's that data. But anyway, like I said, it doesn't matter. We're going to test whatever this column is, this Y2009 column. We're going to test whether or not it's different in Africa versus, what other continent do you want to compare it to? Australia. There's only one Australia. Go for Europe? Okay. So there isn't a column on here that really talks about the, wait, no there is, right? Former country, FIPS country, 2-digit, country name, long name. I'm trying to see if there's already a column. I don't think there is. I looked through the data shortly, and I did not see, I didn't, okay. So what we're going to have to do is manually select those countries that fall into Europe. So, and we have to create a new table, a new field. So I'm going to add another field. I can't add a field. I believe that is because I copied the data off of the CD, and so it's okay. So now I should be able to open the attribute table and add a field. So it's because I copied it off of CD. I don't know. CDs you can't copy. I mean, you can burn stuff onto them, but once they exist, you can't modify the data that's on a CD. For some reason, even when you move it back onto a computer, it's still in read-only mode. You can change it, but I thought this was easy. So I'm going to add an identifier just called I'm just going to call it region. Okay? So I'm going to call my area region. I mean, my thing region. So I have a column called region. And I'm going to select Africa, all the African countries. I'll hold down the shift key. Oops, that doesn't work. How do you add to the selection? I think it's control. Nope. It's got to. I'll just select that. I could just create a box that that would let me select by region. But here we go. I'm going to take Spain out, which includes the Canaries. But I've got all the rest of those African nations there. And now I can calculate in to that a region code. I'll just call it 1. So now I've got all the 1 values. I have to do the same with Europe. I'm going to include Iceland. So I'm going to get all these guys. Take that guy back out. See if I missed any countries. So I've got Russia included. Should I leave it included, or you think I should take it out? Doesn't really matter. What about Turkey? I'm going to include Turkey. They're part of NATO. They like to say they bridge Europe and Asia. So I'm going to shift. Oops. I'm going to shift click, add Turkey, and I'll leave Russia. So I'm going to call this region 2. And then once I do that, the idea here is that I'm going to take the average value from 1 and the average value from 2 and use those to calculate the values. So one thing that I could do to make the data a little bit easier to deal with is I could select again, select by value, select by attributes, and say if the region is greater than 0, it's going to select all the areas that I want. That's my study area. So I can export that data and call this, I'm gonna put it up in just CTEMP QM. I'm going to call this compare dot shape. So that's what it looks like. It contains all those countries. Okay. Okay, so one reason that I might want to do that is that now I have every value, and I could arrange them by value and calculate the ranks. To do that, I think that's going to be a little bit easier in Excel. So I'm going to open up the DBF file, and that is under CTEMP quantitative methods, and I got the DBF file. And then, so that I don't accidentally overwrite this file, I'm going to save this as an Excel file. I'm going to call it just compare.excel. And then just to kind of, I want to keep something. I want to keep one of the names, but I'm going to delete a lot of this other data. I could always tie it back in using a unique field. deleting some of the columns. Actually, that's a good enough column right there, that country name column. Ooh, it's huge. Maybe that was a bad idea. Control Z. Yeah, I'm gonna delete country name because this is kind of annoying. Keep long name. Then I've got this country code. Oh, that's really big too. Okay, you're getting deleted too. All right, so now I've got this data, and I'm really only concerned with year 2009. Another thing that I could do, though, in case I wanted to calculate these later, is hide those columns. Oops, I'm gonna hide this one too. All right, so now I've got just 2009, the region, and the long name, just in case I'm curious. Okay, so in order to, let's do the man Wilcox first. One thing that I want to do right off is delete anything that has a zero value, because a zero value in this case means no data, and it actually is going to cause issues. And most of these no datas are actually countries in the sense that well, Puerto Rico would fall into this category. They are countries, but they're not self-governing. You know where Faroe Islands are? It's like, you know where the Shetlands are? You know where Iceland is? So between Iceland and Scotland, there's a group of islands. There's actually several groups of islands. Some of them are closer to Scotland, and they're actually part of the United Kingdom. But the Faroe Islands are out there between Iceland and Scotland, and they're part of Denmark. They're a constituency country. They're part of Denmark, but they're their own country. But they're not completely independent. So we're going to delete that because they probably didn't get data from that country. They just included it with Denmark, is what I imagine. I don't know for sure. But we could just sort this. Let's see. Sort. We're going to sort it we're going to sort by 2009, smallest to largest. Yeah, that's a good idea. All right. So you see we got all these zeros. So some of these actually are just really small countries like Andorra and Monaco. But some of them, like Guernsey is an Isle of Man, are actually part of the United Kingdom, but they're not considered part of England itself. Jersey is the same way. You all know what the Vatican City is. But that is a island off the coast of Africa that is part of France. So French, what's that? So French, the equivalent of a state is a department in France. So it's like us saying the state of Hawaii, but if it's a department level, it's considered roughly equivalent. I'm not a expert political geographer, but it's roughly equivalent to what we call a state. France has a few more of those spread throughout the world than we do, actually. The things that are kind of like states. Because we just have Hawaii. We also, the United States also has other territories, but they're governed a little bit differently. Right? You got Puerto Rico, and that's a little different even than Guam. All right. Okay, so we've got this column now, and it's all cleaned up, ready to go. And we've got the region. So one thing that we could do now, since it's organized by value, is that we could just type the word rank in, and I'm going to make these not having decimal places. And then we could fill this down, and we'll have the ranks. So these are the ranks of all of these values. All the ranks. Now, if there are any true ties, we probably should fix them, but we're going to assume there aren't any ties. I don't think there are going to be ties because these numbers look pretty good. I wish these were female labor force participation values, but they don't look like that. They look like maybe human development index values or something that's correlated with the highly developed or low developed countries. So we probably are going to get a big difference between Europe and Africa. So we said that Africa was 1. So what I want to do is we just need to pick one or the other to come up with to use the test statistic. So let's just say that that Africa is the one that we're going to pick. We're going to compare Africa to its expected values. So we do need to find out. We need to find out how many countries are left in Africa after we deleted some of them. And then we need to find out what their average rank of the African countries are. Then we also need to find out what the total number of non-African, or in other words, European countries. So one thing that I like to do is create a new column called is Africa and say if this value equals 1, then give it a value of 1, otherwise give it a value of 0. So now when we fill this down, it's going to give us a 1 or a 0 depending on whether or not that country is in Africa. Okay. And so the sum of this column will give us what? What's the sum? What's that? Yeah, the count of African countries, exactly. So we've got 51 African countries. All right. And how many total countries do we have? 2 to 91. So this is N1. This is going to be N2. So I said so the 90 countries total. So this is equal to 90 minus 51. So there are 39 countries in Europe, is another way to say it. 39 countries in Europe, 51 countries in Africa. Okay? So the next thing that I like to do when I'm doing this test is have another one that it's going to give me the rank if it's equal to 1. So what I can do is say rank, I'll just call this the rank T column. And I'm going to take is Africa and multiply it by the rank. So if the African rank, if it's in Africa, I'm going to get the rank. If not, I'm going to get 0. See that? So it's pretty obvious that we're going to all the low numbers were up there, right? Only the highest value is 70 for the territorial collectivity of Mayonet. I didn't even know what that is. I knew what Réunion was. But I'm curious. Okay, so it's another French department. I don't know why it did have that data and Réunion didn't. So it's just above Madagascar. Here's the one that we eliminated because there wasn't any data. And then Mayonet was over there. Okay. So anyway, that they've got pretty high up there on their values. Okay. So now, if I take the sum of this column right here, I'm going to get the sum of all of the ranks, right? Because Because if it's a 0, I get 0 plus anything is anything. Like, okay, 0 plus x is always x. So if those zeros don't hurt. So this is the sum of all the ranks. Should be. Why isn't that working? How come that's 0? Equals the sum. It should not equal 0. That's really weird. Maybe because I'm multiplying. That's weird. I guess it's like adding them up and multiplying them. So to deal with that, we could create a new column and just copy those values in. Control C, paste copied cells, paste just the values. Oops. I'm going to paste just the values. So now I get 1385. So that's the sum of the values. Now, I actually want the mean of the values. So how do I get the mean ranks from the sum? And then this is n. It's just a division problem, right? Yeah, exactly. So this right here is going to be W. It's going to equal this divided by that. And that's going to be the W for I, which I'm just going to call W because the other one's the W for no, that's the, so this is going to be the expected value. I'm just going to write expected. So how do I calculate the expected value? I calculate the expected value as that formula. So it's the number of samples multiplied by the number of samples in the one group plus the number of samples in the other group, which is just the total number of samples, plus 1 divided by 2, and I'm going to put this guy right here and another. Let's make sure that's the right formula. Looks right. Oh, I was going to put this guy out here. Okay, same math. All right, so so that is what we should expect for the average rank. Right? N1 plus I'm just looking at my math because that number is really, really big. Making sure I'm right. 51. The mean rank. 51. That number's not right, is it? divided by 2. Well, I guess that's the number. I'm gonna put in the actual numbers here. $51 is the number. I'm going to break it apart. So this is just the mean rank. Okay. No. I was wrong. Right? This is actually, the sum is actually what we want, not the mean. The mean was just calculated for fun. So W is actually this number right here, and this is just the mean rank. So the W expected value is what we said it was, which would be this times this plus 1 divided by 2, parenthesis, why did that mess up? Oh, it's because Excel needs the multiplication sign. Okay, so this is the value, this is W for the average countries. This is what we expect if the data was if they were random ranks. This is what we would expect. So that value is very much larger than that value. So my guess is that we're going to get, well, let's say, sorry, what the formula is for the rank. Okay, sorry, I should have gone over that better. The formula for the ranks is simply the highest to the lowest. And we just take the very highest value or the very lowest value and just start numbering them. So this is the in our case, the lowest. It doesn't matter if you go lowest or highest, as long as you understand what you're doing. So this is the lowest, or in other words, the poorest country. I'm pretty sure these are even developing there. There is a function in Excel, just fill down. So I sorted them on this column. And then all I did was I started typing 1, 2, and then I just filled down and got the rest of the values. Filled down to the bottom. That's a good question, though. Okay, so the question I was about to ask is, we're going to calculate a t-value from these values. Look at how big they are, difference they are. Knowing that we were probably going to be able to reject the hypothesis that they're equal, what should our t-value? Should our t-value be relatively large or relatively small? In this case, it would be a z-value. No, and not just that. The man wouldn't only use z-value. So what will our t-value be? What would we expect it to be? Would we expect it to be way over in one of the tails, or would we expect it to be in the middle? Yeah, we want it, I mean, not we want it. We expect it to be way out there because these values are way off. They're large differences. Now, the standard deviation will tell us, which will be used to calculate the standard error, will tell us if even large differences could be expected because there's so much variability in this data. So we'll have to see, but just kind of giving this a look, it's going to be a problem. So we're going to calculate the SW, and that's going to be that formula, which is equal to SQRT, and it's going to be N1 times, you've got to remember to use the times symbol, times the this plus 1 divided by 2. Put this around there. I need one more parenthesis to close it, to close the square root. Okay, so that's our standard deviation of our W's. You got that one right. It's always divided by 12. Oh, did I do that by 12 or by 2? I think I did it by 2. 12. All right. There we go. Much better. Okay, so let's calculate the test statistic. That would be this minus this divided by this. It's a pretty straightforward test statistic. And then that produces a z-value. Look at that z-value. 0.76123. What's that? What's this number in if that's a z-value? Standard deviations. Where is that on a normal distribution? Really, really, really far away. In fact, I don't even think we're going to be able to find the z-value on the table. No, it doesn't exist. It only goes out to 3.5. So it's so far over there that the actual p-value, in other words, the area under that curve, is going to be 0.000000 way out there. And we're going to get a value. And of course, we're going to be able to reject the null hypothesis that these populations are equal. They're not equal. Okay? Because we're looking at some, poverty index. I wish I knew what it was, but it's not female participation score, and it is it's life good, what it says, and we get a value that's way over there for that Mann-Whitney test. It could be. Could be life expectancy. Here's the data in Excel. Let's see if there's another. Life expectancy at birth. Yeah. Yep, you're right. I didn't even think to check and see if there was another page. Life expectancy at birth, which it should be female labor force participation, but I think the wrong data slipped onto the CD.
So then that p-value tells me that the life expectancy at birth is not different for those two. It tells us that it is very different.
It is very
for those
good.
two.
Yep. Yes, and so, just one more time, the alpha value that you choose is just where you're comfortable being wrong. If you want to be right 95% of the time, you choose 0.05 as your alpha value, okay? And so you're comparing that value, which is 1 minus how many times you want to be wrong. You're comparing that to your value, your p-value that you got. So if that p-value is bigger, then you do what? If it's bigger than the alpha value, then you accept. You do not reject the null hypothesis. You say, yeah, they're the same. If it's smaller, then you say, yes, those are different. And in our cases, yeah. And these are way different values. Africa is way different than Europe. It's like, we didn't even really, we couldn't have looked it up. Didn't even exist, wasn't there. Okay. I did, now that was the what do you call it, the Mann-Whitney, the Mann-Whitney test. But we could have done this doing a t-test. Okay, I'm gonna take the all the data. I don't really need to take the data off of here, but I am. Make sure I don't have any data down here. Okay, yeah. So I'm gonna save this as. Make sure, what do I call the sheet? Sheet 1. I'm going to save this as compare dot, I already have it saved. That's right. I'm just going to hit save. So now I've got this other sheet called sheet 1. And we could calculate all this stuff to calculate a z statistic, but it would be cumbersome, right? So there are the tools to do that. And after spring break, we'll use like SPSS more, and also I'll demonstrate how you can do it in Python. I'm going to demonstrate this one real quick as a Python script. So I've got my data set up here. I need to do a few things. I need to change this so that it actually reads the Python data. The data I just created. Compare. It is called sheet 1, right? I want to do 2009. Let me see if this will work. Yeah. Okay. Oh, XLX. Looks like they're Is this where it's failing? In my example that I made earlier, I had text columns. It looks like it's failing right there. GF region equals, is it called region? Okay. Since I can change this, I'm going to, because it'll work better for my example. I'm going to sort, again, based on the region variable. And then I'm just going to replace all the ones with A's. And the 2's I'm going to replace with B's. And then, do I save it? Save it, go back here. It's still having a problem. Printed all of the regions. That's what it is. I just forgot that in Python it's a double equal. I think I'm all set. Yep. Okay. I didn't actually have to replace those with zeros. My mistake was that I forgot Python had double equal values. Okay. So I just need to copy this. What did I call the other ones? B. I don't know why I should have made it E. B, U, set 1, set 1, set 1, set 1. Okay. Fine. I don't need these print statements in here. So this basically just sets up, in almost every program, whether or not it's a GUI interface or Python like this, the trick will be organizing the data correctly. So what I've done is created a column, I mean, not created a column, I've taken the data out of column 1 if it equals a B. I've taken it out of column 1 if region equals A here. So I've basically separated out the A's and the B's. And I'm going to run this. I think it's going to work this time. Yep. Okay. So here is the results of a 2-sample t-test that I didn't do by hand. Okay. Because there's a lot of data, so doing it by hand would be a lot of work. But see the p-value? E to the 24th, so there's 24 zeros in front of this p-value. So they're not from the same group. They're definitely different. They don't equal each other. P-value is way out there. That's the p-value from that. Here's where you could set if there's equal variance. So I can change equal variance, and for this data, I'm not sure that it'll make much of a difference, but you can see that you can see how here, when we said that the equal variance was false, we got a different value than when we got the equal variances are true. Of course, it's actually not that different, but the statistic is a little bit different with equal variance. Okay. So that's organizing the data. I wish we had the data on people. I mean, on the email participations. That data seemed more exciting. They calculated that. And look what's interesting here is that from this formula, did they assume the variances were equal or did they assume they were unequal? Yeah. So you have a separate variance estimate, so they assumed that the variances were not equal. So when you do some of these, there are a few that you're going to do by hand, but they're not quite as many observations for the homework. And so you can use the single variant estimate or the other one, the pooled variance estimate. Okay, so we're back over here. There's only one more test that we need to talk about. I know there's a ton of slides left, but I think we can get through them. So there's a 2-sample difference in proportions test. So the difference in proportion test is looking at things where either there's in this case it says a dichotomous, a binary variable. There's only 2 possible outcomes. So that's why in the beginning class I gave you an example. Do you believe that global warming is impacting the Earth? Okay, so that's 2 possible outcomes. It's a yes or a no question. Or it just be a true proportion of something. Okay, the proportion. I guess it's still very similar. So the people that were affected by a certain disease. You can still boil that down to being a yes or no question. Presidential favorability rankings are an example. You compare 2 different states That would be an example of a two sample difference in proportion. Comparing two states, or comparing the states to a nationwide, one state to a nationwide sample, and say, is this state really different from the rest of the nation, or is it its own, or is it very similar? Hours charged between hours changes between weekend visitors and weekday visitors. You can collapse levels. So if you've got data where you've got oppose or favor, you collapse it in there. You always have to choose one or the other. It's kind of like the Wilcox test. You're going to choose one or the other. You're going to choose to test whether or not one group is different than the other, but you do have to label one P1 and one P2 because the formula works out that way. But you're going to get the same statistic whether or not you choose one versus the other. You just need to make sure you use the variance from the one later on. Okay. So the null hypothesis is that the proportion of people or things or whatever in one group is the same as that proportion of another group. So the alternative hypothesis again can be one tail or two tables. So here it says, does the proportion of elderly adults in favor of capital punishment differ from the proportion of young adults in favor of capital punishment? That would be two tails. If your hypothesis is there's a greater proportion of elderly adults in favor of capital punishment than young adults, that is one tail. Again, same thing always applies. The way that this works, if you go back to last chapter, you'll see the steps. You calculate your test statistic, you then calculate a p-value, and you compare that to the alpha value, and if it's smaller than the alpha value, you reject it. If it's greater than the alpha value, you accept the null hypothesis. So all that part is the same. Okay? All right. So here is the method for calculating the standard error. And the standard error is got a lot of numbers in it, but it's fairly simple because we're just looking at, here's the p hat means the major proportion values. And then we've got the ends, the number in each group. Here's the pooled estimate of the focus category for the population, calculated as that number. So you calculate this first, and you put the p-hat in there. So, the number of samples times the proportion plus the number of samples in the other group times the proportion for the other group divided by the number of samples plus the number of samples from both groups. That's the p-hat value. So here's the test. It can be one-tailed or two-tailed. Here's an example that they gave from the book. I do think that they have at least attempted. I don't know if the data is there. They have the obesity. This one I didn't test as much, but this looks like it is very similar to the same data. Okay. Change in obesity percentages. So we're going to test. We're going to have a hypothesis that the obesity level did not change, but it was the same. Okay. So we've got two different samples. Here's a scatter plot showing the proportion of obese in 2000 and the proportion of obese, or the change in obesity from 2000 to 2010. So there's no strong relationship. Okay? So does obesity in 2010 relate to how much change there was? Okay? Strong relationship. But we want to test and see if just the amount of obesity proportions changed. So here's the work table for the two sample difference in proportions test. They just plug the numbers in. And let's look at the z-value. What's the z-value there? Is this, if we go look that up, are we going to find that value on the table? No, because it's 7 standard deviations away. We just did one of those. It was 7 something. Okay? So the associated p-value is 0.00000, and it's not even on the chart. So what does that mean? Does that mean we accept or reject the null hypothesis? What you said reject, right? Yes, it does. It means we reject the null hypothesis, which in this case, what was the null hypothesis? It has to do with obesity. Is it stated there? It's just the, comparing Alabama adult rates. So this is just for Alabama. We don't have that value in the. So it's looking at the obesity rate change. So were they equal in 2000 and 2010? Well, let's look at the percentage. It went from 0.23 to 0.32. And that's a 10-year period. Dang. That's a big difference in 10 years. 30% versus 23% of the population. And what we found was that that is a significant difference. I mean, there's no way those are from the same population. People are significantly fatter than they were in 2000. I know I'm probably significantly fatter than I was in 2000. I actually went through a dip, depending on when I measured it. Tried hard for a little while. All right. So that's what that tests. Okay. Now there's one last test to talk about. What happens if we have samples that are actually taken on the same exact entity twice? So if we just did that fat population study, it'd be as if we found the exact same person and found that if they had gotten larger. It's a little bit different test. In this example, we just sampled, here it says we sampled about 2,000 people in 2000 and about 7,000 people in 2010. Okay? We sampled those people, and they weren't necessarily the same people. Of course, it was a random sample, so there's always some possibility that we sampled the same person. But that's different than what we're talking about now. This is, we're looking at 50 cities, let's say, and they're the same 50 cities in 1960 versus 2000. So, or this is the other example. We sample a bunch of people. We ask them how many miles they drove per week for a year. And a year later, we do the same thing. And gas prices went up, and we want to find out if, on average, people drove less because gas prices went up. So here, in this case, our two samples are not independent. They're dependent. Sample A determined who was going to get picked in sample B. We only really draw one sample. So we don't use the numbers from the two sample t-test to do that. Okay? So when it's matched pair, what we do is actually we don't take in the miles per driven one. We don't take the number of miles and find the average, and the number of miles and find the average. We just take each person and we calculate the difference between the miles driven for sample A and in sample B, or time A and time B. So that's where we say we calculate the difference between each matched pair and then find the mean difference. The differences are small. The average mean is going to be close to 0. If the differences are large, the average difference will be a large value. Okay, and again, the sample, the statistic here is testing whether or not there is a change, change in the values. Now you calculate the standard deviation in a little bit of a convoluted manner, the standard error here, but that's the formula down there, and that's how it builds up. But the difference, the delta, is easy to calculate. You just take all the differences and find the average distance. All right, so let's look at this formula down here. So this formula here is taking the sum of all the distances, the differences squared, minus the sum of those distances squared divided by n. Okay? And then we take all of that divided by n minus 1 and take the square root to get the standard error. And that value is what we use to use on the denominator here. Here's a work table to get through it. So here we've got fish. This is the example I was talking about at the beginning. We have fish in a tank. So we sampled a bunch of fish, we put them in a tank. We weigh them, we give them some hormone treatment, and 1 year later we weigh them again, and then we calculate the difference after 1 year. I don't know why they didn't assume that these 10 fish were grown. Maybe they know what an adult is. It's not supposed to grow anymore. But let's look at the differences in weight after 1 year, and we get these numbers. These are the numbers we're actually going to use. We don't use these numbers. These are the differences in weight after 1 year. Okay? 10 fish, before and after hormone treatment. So we look at that column. So the average distance is taking this column and just finding, the average difference. Taking this column and getting the average. So that's easy. I don't have that much time left, but if I was going to do this in Excel, I would take these values, this column, and calculate the average, and I would get the average value here. No, that's not the average. It's the average delta. Well, the average delta value right here is 1.52, so that's the average value. That's the average of that column. That makes more sense. Okay, it's 1.52. Notice that we didn't actually use this 4.97 value, 4.94 or this 6.46. We didn't use that anywhere in the formula. Like I said, we don't use those numbers, but they included them for fun. But the D bar here, the average difference is right there, 1.52. Okay, and then we calculate the denominator by taking that value and plugging it into this formula. Okay. And we get 0.82 divided by the square root of n minus 1 is 9. Why 9? Okay, why do we use 9 there? What was n? 10. What does n represent in this case? All the 10 fish. And so we get a test statistic of 2.96. Okay? And that's in standard deviations. And so 2.96 is let's go look at the table for that. Now is this this is a t-table. 2.96 with a degrees of freedom of 9. Degrees of freedom 9. the T was 2.96. I'm going to go 2.90. And I get 0.4912. I said 2.96. I might go to 3.0. 4925. 4925. And so we need to calculate the p-value for one tail would be minus that. 4925. .4925. What do we subtract that from if we just want to get one tail? If we just want to get one tail, because this is just telling us the area under half the curve, basically. Yep. So we go this minus this, and we're going to get one tail. If we want to get a two tail, we could double that. They calculated it as 0.01, which they probably just rounded. Okay? 'Cause in our table, I get that value. Now, what if I did 0.29, 9 degrees of freedom? That's 4.4912. 0.88, it's a little bit higher, but still, I actually have seen people that usually round p-values to two significant digits. So, in any case, rounded to two significant digits, do we reject or accept the null hypothesis? The p-value is really small. It's not as small as we've seen, but it's small enough to, first of all, we do have to say, let's say that we're interested in being right 95% of the time. We reject. Yep, exactly. So what does that mean? Are the fish weighing differently or not weighing differently? Yeah, they're weighing differently. They're significantly different. Okay? Now, if we were interested in being right 99% of the time, rounding that becomes a little problematic because we're right on the value. Okay? We're dead on it. So it's 0.01. But, well, in our case, where we know that we rounded it, we would say that we still reject it, even at 99% confidence. We would reject that. Yeah. All right. Now you can do a Wilcox match pair signed rank test. In other words, what this is looking at is if we looked at crime and we looked at all the ranks, and then we looked at those same areas and we looked at their ranks in time two, that would be an example of using the match paired signed rank tests. And I'm not going to do an example of this, but your book has this example here. And again, we'll look at this value. This value for Z that we got once we plugged all the numbers in. Here we had indoor water usage. Sorry to jump back here, but this is indoor water usage per household. These are all the same households. And so we're wondering, we created a program and it did something. Okay? It changed the way people use water. Here's the change in the water use, and there's the rank. Okay? The rank. And so this is the rank change. So this is the biggest change right here. Notice they did do the 5.5 to go to 2 with the same value. So there's the biggest change, second biggest change, and so on. All right, so we're going to see if this test statistic allows us to reject the null hypothesis, which in this case did the change in water usage, was it random, or is it actually resulting in a change in water usage? Okay? I mean, negative 1.245, notice this is still a z, so look at the z table. 1.245. What's the p-value we should get? And let's make sure that our values match up with the book, which I've noticed. Elda's not here, but I have noticed that there are some errors. But let's see if this is one of them. Okay, so what value did you get, Ashley? I noticed you were already looking. 1.245.
1.24 is 0.3925.
3925, yeah, I think you're right. Okay, and the p-value is actually the area on the other side of the curve, so we actually need to subtract that to get the area on the other side of the curve. 3925, and we're going to get a different value. It's still going to, I think, be the same result. 0.3925. How do we get the actual p-value? 0.5, you're right. Minus that value equals 0.5 minus this value. 1.07, so it's the same value, just rounded a little bit different. Well, not really. They probably had access to a better table that got out to more significant digits. But anyway, rounded to two significant digits, it's really similar. Because this would be rounded up to 7. Ours are technically rounded up to 8, right? Like the value we found. 1.007 would be rounded up to. It's very, very similar. Okay? So, in any case, is the value, is this going to cause us to accept or reject the null hypothesis? Yeah, the p-value. But you have to decide what alpha value we're using. But no matter, nobody chooses anything more than 0.10. So even at 0.10, we're getting close, but we're not rejecting. So we're accepting the null hypothesis. Okay. So our program implementation didn't do anything. It didn't significantly help. Okay. There was some change in water usage, but it wasn't significant in the sample. In other words, if we drew another sample, we could have gotten numbers that were closer. All right. And that is the last slide. It is close to noon. So next week is on the schedule a test, right? So we're gonna take a test because actually they asked if I could. Chris Hare is doing his. They said the only time we can meet is Wednesday at 11 o'clock. So we're going to take a test, and that way, hopefully we'll be done by 11. If not, we'll find somebody to come in here and submit. Hey, has Corey been here? Is Corey here? Okay. He hasn't been here for a couple of weeks now.
Yeah, that's only before last month.
Okay.
Okay, so.
Yeah, I'm just wondering about taking the test, proctoring it down there, but we'll find something to do. Okay, so so for the test, we're just going to cover what we've covered up to this point in class. But I'm not going to have you calculate a bunch of things and get a result. Rather, be able to apply and know which tests will help with which types of problems. And then also, you should know about a little bit of the kind of like the reason why I hit this so hard today was because I want you guys to be able to know when we set up a test and we get a value, like if I say this is the value and this is the p-value, you should be able to know whether or not you reject or accept that null hypothesis. So you should know what a null hypothesis is, what a one-tailed test encompasses, and what a two-tailed test encompasses. So on the test, you may get a test statistic and have to look up a p-value, in which case you can look that up. I'll give you the material to look that up. And then know whether or not you accept or reject it. But on the test, you won't be like on the homework part. You won't be calculating large sets of numbers. There won't be any of that. What's that? Yeah, there's a few of you. If you want to show me what you got beforehand, I can say, you might want to give me a copy too, just in case the table value is slightly off. Like, after the test.
Oh.
Just, if you are using a different table, bring the table and give me a copy, just in case the table values are wrong. Different, not wrong. Different, so that I can test that. Sorry. No, you won't need to memorize the formulas actually for any of them. No, you don't have to memorize formulas, but you have to know which tests. Which tests go with which type of scenario, and then you might get a work table like this, get a value, and have to decide whether to accept. You will get. Well, there'll be questions that are like that, where you'll have a work table, and you can assume that all the numbers are correct, and you'll get a z value, and you won't be given the p value, and you'll have to get that yourself. And then you might be asked, for example, do we accept or reject the null hypothesis? As a separate question. You could be given a scenario that included so one type of question might be given so that you have, and they'll be clearly stated, a population compared to a sample where the sample data is the number of people that were happy about a certain law. Okay? What type of test? And we'd have to say that would be a one sample difference in proportions test. You wouldn't have to memorize the number that goes along with that. But I mean, not the number, the math. You don't have to actually work through it, but that would be an example of a question. And then from earlier parts of the chapter, from earlier parts of the book, there are some questions on the test, just calculating very, very simple things like just a mean and a standard deviation. So that's on there, but not working through a whole problem. Yeah, I will put the equation for standard deviation in there. Yeah, why don't I do this? I didn't have time yet, but tomorrow I will work up a review sheet. And if you have questions, you can either come see me personally. I'll be here on Tuesday next week, or you can send me an email. I'll be here on Tuesday from 9 to like 3. All right. Yeah, I'll type up a review sheet to make it a little bit better. Sound good? Okay.